Vacuum metastability. Vacuum metastability represents one of the most fundamental threats to existence itself. The Higgs field, which gives all particles their mass, currently sits in what physicists call a false vacuum state. This means the field exists in a temporary energy configuration that appears stable but is not the lowest possible energy state. Think of a ball sitting in a shallow depression on a hillside. It looks stable, but if disturbed, it could roll down to a much deeper valley below. The true vacuum state would have completely different physical properties. If the Higgs field were to spontaneously tunnel to this lower energy state, it would create a bubble of altered physics expanding outward at the speed of light. Inside this bubble, the fundamental constants of nature would change. Atoms would no longer bind together the same way. The strong nuclear force might weaken. Electromagnetic interactions could cease to function as we know them. This transition would happen without warning. There would be no advanced signal, no gravitational waves, no electromagnetic radiation to alert us. The bubble wall would simply arrive, rewriting the laws of physics as it passed. Everything in its path, galaxies, stars, planets, and all matter, would be instantly restructured according to the new physical laws or simply cease to exist. Current calculations suggest our vacuum state is metastable, meaning it could theoretically decay, but the probability is extraordinarily low on human timescales. However, high-energy events like cosmic ray collisions or the formation of microscopic black holes could potentially trigger this transition. The uncertainty lies in our incomplete understanding of quantum field theory at the highest energy scales. Primordial black holes. Primordial black holes formed in the first fraction of a second after the Big Bang, when extremely dense regions of space collapsed under their own gravity. Unlike stellar black holes that form from dying stars, these ancient objects could have masses ranging from less than a gram to millions of solar masses. They represent some of the earliest and most mysterious structures in the universe. These black holes formed when quantum fluctuations in the early universe created regions dense enough to overcome the outward pressure of radiation. The process required density variations of at least 30% above the average cosmic density. Most of these fluctuations were smoothed out by cosmic expansion, but the largest ones collapsed into black holes within the first microsecond of cosmic history. What makes primordial black holes particularly terrifying is their potential abundance and invisibility. Theoretical models suggest they could make up a significant portion of dark matter, the mysterious substance that comprises 85% of all matter in the universe. This means millions or billions of these invisible gravitational traps could be scattered throughout our galaxy, drifting silently through space. Small primordial black holes, those with masses less than a mountain, would have evaporated completely through Hawking radiation by now. But larger ones persist indefinitely. A primordial black hole with the mass of Earth would have an event horizon only 9 millimeters across, making it virtually impossible to detect unless it actively consumes matter. The most disturbing possibility is that one of these objects could be wandering through our solar system right now. Unlike stellar black holes, which announce their presence through X-ray emissions from heated matter, a solitary primordial black hole would remain completely dark until something crossed its path. Strange stars. Strange stars represent a theoretical form of matter, so exotic that they challenge our understanding of nuclear physics. These objects would form when the intense pressure inside a neutron star becomes so extreme that it converts ordinary matter into strange quark matter, creating a fundamentally different type of stellar remnant. Normal matter consists of protons and neutrons, which are themselves made of up quarks and down quarks. Under the crushing conditions inside a neutron star, these particles can be compressed beyond their normal limits. If the pressure exceeds a critical threshold, the up and down quarks transform into strange quarks, creating a soup of free quarks rather than bound particles. Strange quark matter has properties that defy conventional physics. It would be absolutely stable at any pressure, meaning it represents the true ground state of matter rather than the atoms we observe in everyday life. This stability comes from the strange quark's ability to occupy lower energy states than conventional nuclear matter, making strange matter more tightly bound than even atomic nuclei. The terrifying aspect of strange stars lies in their potential for conversion. If strange quark matter is truly more stable than normal matter, then any contact between strange matter and ordinary matter would trigger a chain reaction. The normal matter would convert to strange matter, releasing energy and spreading the conversion process outward like a cosmic infection. A strange star would appear similar to a neutron star from a distance, but its surface would be fundamentally different. Instead of a solid crust of atomic nuclei, it would have a smooth surface of pure quark matter. The boundary between the star and empty space would be sharp and well-defined, unlike the fuzzy atmosphere of normal stars. If strange stars exist, they could be scattered throughout the galaxy, indistinguishable from neutron stars until detailed observations reveal their true nature. The possibility that ordinary matter is not the most stable form of matter in the universe suggests that everything we see around us exists in a metastable state, vulnerable to conversion by contact with strange matter. Kugelblitz, black holes. Kugelblitz black holes form not from collapsing matter, but from pure concentrated energy. The name comes from German, meaning ball lightning, and describes a theoretical black hole created when electromagnetic radiation becomes so intensely focused that it curves spacetime enough to trap light itself. This represents one of the most exotic ways a black hole can theoretically form. Einstein's mass-energy equivalence principle states that energy and mass are interchangeable. When enough energy concentrates in a small enough region of space, it can create the same gravitational effects as an equivalent amount of mass. For a Kugelblitz to form, the energy density must reach approximately 10 to the 67th joules per cubic meter, a concentration so extreme that it exists only in theoretical calculations. The formation process would require focusing enormous amounts of electromagnetic radiation, such as gamma rays or high-energy photons, into a region smaller than the resulting black hole's Schwarzschild radius. At this point, the energy itself becomes gravitationally bound, creating an event horizon from which even the light that formed it cannot escape. What makes Kugelblitz black holes particularly unsettling is their potential for artificial creation. Unlike stellar black holes that require the collapse of massive stars, a Kugelblitz could theoretically be manufactured using advanced technology capable of concentrating sufficient energy. This raises the possibility that sufficiently advanced civilizations could weaponize black hole formation, creating gravitational weapons of unimaginable destructive power. Natural Kugelblitz formation remains highly speculative, but certain extreme astrophysical events might generate the necessary energy concentrations. The collision of multiple gamma-ray bursts, the focusing of cosmic rays by gravitational lensing, or the interaction of matter and antimatter in specific configurations could potentially create the conditions for spontaneous Kugelblitz formation. These energy-based black holes would behave identically to mass-based black holes once formed, but their origin from pure radiation represents a fundamental demonstration that energy and matter are truly equivalent at the most extreme scales of physics. White holes. White holes represent the theoretical opposite of black holes, regions of spacetime that expel matter and energy rather than consuming it. While black holes have event horizons that prevent anything from escaping, white holes would have event horizons that prevent anything from entering. These objects exist as mathematical solutions to Einstein's field equations, but have never been observed in nature. The concept emerges from the time-reversed mathematics of black hole physics. If you run the equations for a black hole backward in time, you get a white hole that spews out matter and energy continuously. The event horizon of a white hole acts as a one-way barrier in the opposite direction, allowing matter and radiation to exit but forbidding any external material from crossing inward. White holes would violate the second law of thermodynamics by continuously decreasing entropy in their local region. They would spontaneously create order from chaos, ejecting organized matter and energy into the universe without any apparent source. This creates a feedback loop where the white hole's own emissions prevent anything from falling into it, but also make the surrounding region increasingly chaotic and energetic. Some cosmologists have speculated that the Big Bang itself might have been a white hole event, the ultimate expulsion of matter and energy into an empty universe. This would make our entire observable universe the product of a single, massive white hole that existed for an infinitesimally brief moment before exhausting itself. If white holes exist, they would appear as brilliant sources of matter and energy with no apparent fuel source. They would shine continuously, ejecting particles and radiation at tremendous rates, while remaining completely inaccessible to external influence. The energy output would be enormous and unpredictable, making any nearby region of space extremely hazardous. Naked singularities. Naked singularities represent one of the most terrifying violations of cosmic censorship in theoretical physics. Unlike the singularities hidden within black holes, a naked singularity would be a point of infinite density and curvature exposed directly to the universe, unshielded by an event horizon. This exposure would allow the singularity to interact directly with the outside world in ways that could fundamentally break causality. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that nature prevents naked singularities from forming by always surrounding them with event horizons. This protection is crucial because singularities represent points where the known laws of physics break down completely. Space and time become infinitely curved, density becomes infinite, and mathematical descriptions of reality cease to function. A naked singularity would form if a massive object collapsed without generating an event horizon, or if an existing black hole lost enough mass through Hawking radiation that its event horizon disappeared before the singularity evaporated. They could violate conservation laws, create closed timelike curves that allow time travel, and generate effects that propagate faster than light. Near a naked singularity, the curvature of spacetime would become so extreme that tidal forces would stretch and compress matter in impossible ways. The gravitational field would be so strong that it could tear apart atomic nuclei, but unlike inside a black hole, this destruction would be visible to outside observers and could influence the rest of the universe. The most disturbing possibility is that naked singularities could act as sources of completely unpredictable phenomena. They might spontaneously create matter, emit bursts of exotic particles, or generate gravitational waves with no apparent cause. The breakdown of physical laws at the singularity means that literally anything could emerge from these points, making them cosmic wildcards that could reshape reality without warning. Phantom dark energy. Phantom dark energy represents a theoretical form of dark energy, with an equation of state parameter less than -1, meaning its density increases as the universe expands rather than decreasing. This violates the null energy condition, a fundamental assumption in general relativity that prevents energy density from becoming arbitrarily negative. If phantom dark energy exists, it would drive an accelerating expansion so extreme that it would eventually tear apart every structure in the universe. Normal dark energy, which comprises approximately 70% of the universe, has a constant density as space expands. This creates a repulsive gravitational effect that accelerates cosmic expansion at a steady rate. Phantom dark energy would behave differently, becoming denser and more powerful as the universe grows larger, creating a runaway acceleration that grows stronger over time. The equation of state parameter, denoted as W, determines how dark energy behaves during expansion. Normal matter has W equals 0. Radiation has W equals 1/3. And cosmological constant dark energy has W equals -1. Phantom dark energy would have W less than -1, meaning its pressure becomes more negative than its energy density, violating fundamental energy conditions. This violation leads to catastrophic consequences for the future of the universe. As phantom dark energy becomes denser, its repulsive effects grow stronger, accelerating expansion at an ever-increasing rate. Eventually, this acceleration would overcome all other forces in nature, including the strong nuclear force that holds atomic nuclei together. The timeline for phantom dark energy destruction would follow a predictable sequence. First, galaxy clusters would be torn apart as space expands faster than gravity can hold them together. Then, individual galaxies would dissolve as stars are pulled away from each other. Solar systems would disintegrate as planets are ripped from their orbits. Finally, in the last moments, atoms themselves would be torn apart as the expansion of space overcomes electromagnetic and nuclear forces. Current observations of cosmic acceleration are consistent with a cosmological constant, but the uncertainty in measurements leaves room for phantom dark energy as a possibility. If future observations detect W becoming more negative than -1, it would confirm that the universe is heading toward this ultimate destruction, with no possible escape or prevention. Closed timelike curves. Closed timelike curves represent regions of spacetime where the geometry becomes so warped that time loops back on itself, creating paths through spacetime that return to their own past. These mathematical solutions to Einstein's field equations allow for the theoretical possibility of time travel, but they also create paradoxes that could fundamentally break causality and the logical structure of reality. The curves form when extreme gravitational fields or exotic matter configurations bend space-time so severely that the normal flow of time becomes twisted. In these regions, an object following its natural path through space-time could theoretically travel into its own past without exceeding the speed of light or violating local physical laws. The curvature of space-time itself provides the mechanism for backward time travel. Several theoretical scenarios could generate closed time-like curves. Rotating black holes, known as Kerr black holes, contain regions called ergospheres, where space-time is dragged around so violently that closed time-like curves become possible. Cosmic strings. Hypothetical one-dimensional defects in space-time could create closed time-like curves if two strings passed by each other at high speed. Alcubierre warp drives, theoretical faster-than-light propulsion systems, could also generate these temporal loops as a side effect. The existence of closed time-like curves would create grandfather paradoxes and other logical contradictions. An observer could theoretically travel back in time and prevent their own birth, or deliver information to their past self that they only learned by receiving it from their future self. These paradoxes suggest that either closed time-like curves cannot exist in nature, or that some unknown mechanism prevents paradoxes from occurring. The Novikov self-consistency principle attempts to resolve these paradoxes by suggesting that the laws of physics would somehow conspire to prevent any action that would create a logical contradiction. Events would arrange themselves so that any attempt to change the past would fail, or would turn out to have been part of the original timeline all along. In cosmological models with infinite time or space, Boltzmann brains become not just possible but inevitable. If the universe continues expanding and cooling forever, reaching a state of maximum entropy, random quantum fluctuations will eventually produce every possible arrangement of matter. This includes countless Boltzmann brains, each existing for brief moments with complete false memories of lives they never lived. The terrifying implication is that if Boltzmann brains vastly outnumber naturally evolved conscious beings, then statistically, you are more likely to be a Boltzmann brain than a real person. Your memories of childhood, education, and experiences would be illusions created by random particle arrangements. The entire universe you perceive could be a false construction of a fluctuating brain destined to dissolve back into chaos within moments. This paradox suggests that either our cosmological models are wrong, or that consciousness and observation work in ways we do not understand. Some physicists argue that the Boltzmann brain problem indicates flaws in our theories about the ultimate fate of the universe, while others propose that conscious observation itself plays a fundamental role in determining which configurations of matter can exist. The existence of Boltzmann brains would mean that most conscious experiences in the universe are brief, isolated, and based on completely false information about reality. It represents the ultimate cosmic horror. The possibility that consciousness itself is mostly an illusion experienced by randomly assembled matter in an otherwise empty and meaningless universe. The heat-death plateau. The heat-death plateau represents the final equilibrium state of the universe, a period lasting incomprehensibly longer than all previous cosmic history combined. After the last stars burn out and black holes evaporate through Hawking radiation, the universe will enter a state of maximum entropy where no further work can be performed and no complex structures can exist. This plateau begins approximately 10 to the 100 power years from now, when the last stellar remnants fade and the cosmic microwave background radiation cools to near absolute zero. At this point, the universe will consist primarily of elementary particles, photons, and neutrinos distributed uniformly throughout an ever-expanding space. The temperature will approach absolute zero, but never quite reach it due to the continued expansion of space. During the heat-death plateau, the universe will be dominated by quantum vacuum fluctuations. These random variations in energy will occasionally create temporary structures, including particles, atoms, and even complex molecules. But these formations will be extremely rare and short-lived. The average time between significant fluctuations will be measured in periods so vast that they dwarf the current age of the universe by factors of trillions upon trillions. The most disturbing aspect of the heat-death plateau is its duration. While the universe has existed for approximately 14 billion years, the heat-death plateau will last for an essentially infinite amount of time. All of cosmic history up to this point represents an infinitesimally brief moment compared to the eternal emptiness that follows. Every star that has ever shone, every planet that has ever formed, and every life that has ever existed will be forgotten in a universe that continues expanding into ever greater emptiness. Quantum mechanics suggests that even during heat death, rare fluctuations could theoretically recreate complex structures, including entire civilizations, with false memories of rich histories. However, these fluctuations would be separated by time intervals so enormous that they would occur less frequently than once per 10 to the 10 to the 50 power years, making them effectively impossible on any meaningful timescale. The heat-death plateau represents the ultimate triumph of entropy over order, a cosmic state where the universe has exhausted all possibilities for creating complexity or meaning. It is not destruction in any dramatic sense, but rather an eternal, unchanging emptiness where nothing significant can ever happen again. Vacuum decay bubbles. Vacuum decay bubbles represent expanding regions of altered physics that could be propagating through the universe right now, invisible and undetectable until they arrive. These bubbles form when the Higgs field transitions from its current metastable state to a lower energy configuration, creating spherical regions where the fundamental laws of nature operate differently than in our observable universe. The bubble formation process begins with quantum tunneling, a phenomenon where particles can spontaneously transition through energy barriers that should be impossible to cross according to classical physics. If the Higgs field tunnels to a lower energy state at any point in space, it creates a small bubble of true vacuum surrounded by our false vacuum. This bubble then expands outward at the speed of light, converting everything in its path to the new physics. The bubble wall itself would be a thin boundary layer where the transition between old and new physics occurs. This boundary would be incredibly energetic, containing enough concentrated energy to potentially outshine entire galaxies as it passes. However, the energy would be released in forms that might not be detectable by instruments designed to observe our current physics. Inside a vacuum decay bubble, the properties of matter and energy would be fundamentally different. The masses of particles could change dramatically, making atoms unstable or preventing them from forming altogether. The strength of fundamental forces like electromagnetism and the strong nuclear force could be altered, causing all chemical bonds to break and atomic nuclei to disintegrate. What makes vacuum decay bubbles particularly terrifying is their complete unpredictability and inevitability. Multiple bubbles could be expanding through the universe simultaneously, each one invisible until it arrives. There would be no way to detect an approaching bubble, no method to shield against its effects, and no possibility of escape once the transition begins. The expansion rate ensures that once a bubble forms anywhere in the universe, it will eventually encompass all of space. Even if a bubble formed in the most distant observable galaxy, it would still reach Earth eventually, though the journey might take billions of years. The universe could already contain numerous expanding bubbles of altered physics, racing toward us at light speed through the cosmic void. Each bubble represents a complete rewriting of reality, transforming regions of space into domains governed by alien physical laws that could make the existence of matter, energy, and structure as we know them impossible. Cosmic strings. Cosmic strings are hypothetical one-dimensional defects in space-time that could stretch across the entire observable universe, possessing gravitational effects so extreme they could slice through planets and stars like invisible cosmic razors. These theoretical structures would have formed during phase transitions in the early universe, when the fundamental forces separated from their unified state in the first fraction of a second after the Big Bang. A cosmic string would be incredibly thin, with a width smaller than a proton, but potentially millions of light-years in length. Despite their microscopic thickness, cosmic strings would contain enormous amounts of mass energy concentrated into their linear structure. A single meter of cosmic string could have a mass equivalent to Mount Everest, creating gravitational effects that warp spacetime along their entire length. The gravitational field around a cosmic string differs fundamentally from that of normal matter. Instead of creating a spherical gravitational well like a planet or star, a cosmic string would create a conical deficit in spacetime. This means that space around the string would be missing a wedge-shaped section, causing light rays and matter to be deflected as they pass nearby, but without the typical attractive force of conventional gravity. If cosmic strings exist, they would be moving through space at significant fractions of the speed of light. oscillating and vibrating as they travel. These oscillations would generate gravitational waves, ripples in space-time that could potentially be detected by sensitive instruments. However, the strings themselves would be essentially invisible, detectable only through their gravitational effects on surrounding matter and light. The most terrifying aspect of cosmic strings lies in their potential for destruction through direct collision. If a cosmic string passed through a planet, star, or any other object, it would slice cleanly through without slowing down or being deflected. The gravitational shear forces would be so intense that they would tear apart atomic bonds and nuclear structure, leaving behind a perfectly smooth cut through whatever material the string encountered. A cosmic string collision with Earth would be instantaneous and absolute. The string would pass through the planet in a fraction of a second, potentially splitting it into two separate pieces that would then drift apart. There would be no warning, no way to detect the approaching string, and no possible defense against its effects. The cut would be so clean that initially, the two halves might not even realize they had been separated until gravitational forces began pulling them apart.